Hello everyone, my name is Sunwoo from KAIST AI. Today, I'd like to introduce our research on graph-level anomaly detection. Let me first give an overview of our research. Graph-level anomaly detection, in short GLAD, aims to find graphs with anomalous node features and topology, compared to the most in the population. Consider the shown graph population. Each graph in the graph population contains a triangle. Now, consider another two new graphs. The first graph also contains a triangle similar to the graph population. However, the second graph does not. Therefore, the first graph is considered as a normal graph, while the second is considered as an anomaly. In GLAD, we aim to find such anomalous graphs. Note that the triangle case is an example, and real-world graphs exhibit much diverse patterns, and GLAD primarily aims to detect anomalies in such general cases. GLAD has various real-world applications as shown in the slide. Many GLAD methods use graph autoencoders, in short Graph-AEs. These methods typically learn to reconstruct the given graph's topology. Consider the shown graph, which has the following topology and node features. Formally, graph topology can be expressed as an adjacency matrix, a matrix representing the connectivity of a graph. Then, Graph-AE is trained to accurately reconstruct the graph's adjacency matrix. That is, it aims to make these two matrices similar. These Graph-AEs use mean reconstruction error as the anomaly score. To this end, it uses element-wise mean squared error. That is, it computes squared error on each element. Then we compute the mean of them and regard it as the anomaly score of this graph. And in the final inference, we regard the graphs with high mean reconstruction errors as anomalies. In this example, red graphs have significantly high mean error. In this case, green graph is regarded as a normal graph, while the red one is regarded as an anomaly. We now move on to the limitations and the proposed method. Surprisingly, we observed that Graph-AEs can better reconstruct certain graphs that are dissimilar from the training graphs. Consider the following training graphs. There is an unseen graph which looks significantly dissimilar with the training graphs. However, surprisingly, the mean reconstruction error of the unseen graph is lower than those of the training graphs. In our paper, we provide detailed theoretical and empirical analysis regarding this phenomenon. Notably, in such cases, Graph-AEs are unable to detect anomalies. Consider the following two graphs. One represents a normal graph, while the other represents an anomaly. Under the aforementioned case, Graph-AEs would have errors for anomalous graphs than the normal one. Since Graph-AE-based GLAD methods regard high mean errors graphs as anomalies, they cannot detect anomalies that exhibit this characteristic. To overcome this, we use the mean reconstruction error as features of a graph instead of directly using it as an anomaly score. We present the second limitation. These similar graphs could have similar mean reconstruction errors. Consider the shown two graphs. Despite their distinct structures, they have similar mean errors as shown in the right-hand side figure. In such cases, again, the Graph-AE-based GLAD methods cannot detect anomalies. Let's consider the left graph as the normal graph and the right graph as an anomaly. The GLAD method may mistakenly classify both graphs as either normal or both as anomalies. To address this, we use multifaceted summaries of reconstruction errors beyond the mean alone to represent each graph. Based on our remedies, we propose a novel GLAD method called MUSE. MUSE represents each graph with the multiple summaries of its reconstruction errors. For each graph, we first obtain their error distributions. Then, we obtain the multifaceted summary of respective reconstruction error distributions. Finally, we use the derived multifaceted summaries to represent each graph. A one-class classifier can then be applied to these representations to ultimately detect anomalies. We summarize our experimental results. Compared to the existing GLAD method, MUSE shows higher anomaly detection performance. In addition, against the training set contamination, MUSE shows the least performance drop. Lastly, MUSE well separates normal graphs from anomalous graphs. We finally present our conclusions. In this work, we study graph-level anomaly detection. We first provide limitations of the existing graph autoencoder-based GLAD methods and propose a new method, MUSE, which overcomes these limitations. Lastly, we demonstrate the superiority of our method through extensive experiments. Our paper and code are available in the shown QR codes. Thank you for listening.